I want to talk about the gamma function. The gamma function is a beautiful extension of the factorials. I'm sure if you're watching this video, you understand some idea of factorials. We can take the factorial of 3, we can take the factorial of 4, we can take the factorial of any positive natural number. But of course, mathematicians were also thinking about what happens when we take the factorial of, say, 1/2. Well, this is why we use the gamma function. It's super powerful and it's actually very mysterious in my opinion. And believe it or not, there's many problems that involve the gamma function. But before we can really dive into those types of problems, let's talk about how this integral here is equal to the gamma function. All right, let's get started. So before we can even prove this statement, we need to establish some properties. The very first property is that this integral of natural log of x raised to the power of n in terms of x is going to equal to x natural log of x to the power of n minus n integral natural log of x to the power of n minus 1 dx. So this is going to be a recurring integral that we're going to see. So why not start off with just the simple natural log of x dx? So we can go ahead and prove this using integration by parts by making our u equal to natural log of x. Our du is going to be 1 over x dx. We have our dv, that's going to be dx, and then we have our v, that's just going to be x. Now establishing the integration by parts, uv minus integral v du, we're going to go ahead and have x natural log of x minus integral of x times 1 over x dx. Now 1 over x or x times 1 over x is just going to cancel out, so we're really just going to have 1 times dx. Now integrating this becomes x natural log of x minus x plus our cheese. Now, a lot of people already knew this property here, but we're going to go ahead and expand this now using natural log of x to the power of 2. So let's just continue and do natural log of x to the power of 2 dx. Well, we're going to do the same thing. We're going to go ahead and start off on making our u natural log of x raised to the power of 2. Our du is going to be 2 natural log of x over x. And then we have our dv, which is going to be the dx. And now our v is going to be x. So let's continue with that ultraviolet voodoo, as I like to call it. So uv minus integral v du is equal to x natural log of x raised to the power of 2 minus 2 integral of natural log of x dx. And so now what we need to do is continue integrating this, and that's the integral of natural log of x, which guess what? We know the answer for that, that's on top. So now our result is going to be x natural log of x raised to the power of 2 minus 2, parentheses x natural log of x minus x, and then we have our plus cheese. Let me just go ahead and sort of distribute that x or the 2 into all these terms. So we have minus 2x natural log of x minus 2x plus our cheese. Wait a minute. I figured, or I'm noticing that this is a negative 2 and that's a negative x. So really this right here should be a positive. So let's just go ahead and change that real quick. And by the way, if you see any errors on here, please let me know in the comments below, and I'll make sure to acknowledge them and then rewrite them. Okay, I think we owe it to ourselves to at least do one more iteration here. So what about the natural log of x to the power of 3 dx? Okay, so I sped it up here, but I highly encourage you to try to solve this on your own. And as you can tell here, we don't want to keep doing that work. If we continue this process, we're going to have natural log of x raised to the power of n dx is going to equal to this property here, x natural log of x raised to the power of n minus n integral natural log of x raised to the power of n minus 1 dx. Now you can technically, I'm assuming, prove this using induction, but we're not going to do that in this case. Hopefully you can trust me and believe me that this is the property here, that whenever we're taking the integral of natural log of x raised to the power of n, it's going to equal this value on the right hand side. So what do we do with this? Well, before we continue, we're going to go ahead and talk about another property here. Okay, we have the second property, and that is that the limit as x approaches 0 of some value x times natural log of x raised to the power of n is going to equal to 0. I would highly encourage you for you to actually prove this property and see that this is true. But now, the reason why we're doing this is because we're going to go ahead and continue, and we're going to now take the definite integral of the values that we found. So for example, we're going to start off with the integral from 0 to 1 of natural log of x dx. So this is natural log of x raised to the power of 1 dx. And you already know that this value is equal to x natural log of x minus x. But there's a problem here. okay, because natural log is not defined at 0. So what we have to do is create a limit as b approaches 0, and then make sure we have our b as our lower bound and then 1 as our upper bound here. So let's go ahead and implement the first fundamental theorem of calculus. We have limit as b approaches 0, and if we plug in 1, for the first term, that's 1 times natural log of 1. Well, that's just going to be 0. Minus 1. So we have minus 1 minus, and now let's go ahead and plug in our b's. We're going to have b natural log of b minus b. So from here, we're going to have limit as b approaches 0 of -1 minus b natural log of b minus b. Now, as we take the limit of -1, that's just going to be -1. The limit of this b natural log of b, you'll notice that this is actually the property up on top. That's property number 2. That's going to be 0. And then the limit of b as b approaches 0, that's just going to be 0. So we're just going to have a value of -1. Okay, not bad. Well, let's try the same thing for natural log of x raised to the power of 2. So from here, I just continue using the limits that we've already found, and we use the first fundamental theorem of calculus to find our values. So let's talk about the pattern. These were our values. We had -1, and then we had +2. And now we have -6, and now we have +24. If you look at these values, they go from -1, +2, -6, +24. Well, there's a pattern here. This is actually going to equal to -1 to the power of n times n factorial. Okay, so when n is equal to 1, we get -1. When n is equal to 2, we get 2 factorial. When n is equal to 3, we get -6 factorial. And then when n is equal to 4, we get +4 factorial. So the pattern continues. So that means that this integral from 0 to 1 of the natural log of x raised to the power of n in terms of x is going to equal to -1 to the power of n factorial. Okay, that's pretty neat. So how do we continue using this so that we can find the gamma function? Well, let's raw dog this. First thing that we're going to do is go ahead and divide the -1 to the power of n to the other side. So we have 1 over -1 to the power of n, integral from 0 to 1 of natural log of x to the power of n dx, and this is equal to n factorial. In fact, if you allow me, I'm just going to change it up a little bit because I'm going to have a lot of work that we have to write. So I'm just going to do n factorial is equal to 1 over -1 to the power of n, integral from 0 to 1 of natural log of x to the power of n dx. Okay, not bad. Well, because we have that -1 to the power of n, we're going to bring it on the inside, and it's going to look like this. Natural log of x over -1, and then all to the power of n. If you use properties of exponents, you'll see that this is actually going to be correct. All right, well, you know what? Maybe we can rewrite it a little bit more and do negative natural log of x to the power of n dx. No harm in that. I mean, we just brought the -1 to the top. Nothing crazy, but we can use that idea for properties of exponents or one of the properties of logarithms and bring that to the power of x. So we have n factorial is equal to integral from 0 to 1 of natural log of x to the -1 all to the power of n in terms of x. Okay, that's actually looking pretty good in my opinion. And then maybe we can change it up perhaps one more time, because now this is going to be integral from 0 to 1 of, check this out, natural log of 1 over x to the power of n dx. All I'm using is properties of exponents here. It's actually really neat how this turns out. Well, now let's go ahead and really integrate this. Let's make t equal to natural log of 1 over x. And if I rewrite this a little bit, if I take the e of both sides, I'm really going to get e to the t is equal to 1 over x. We're going to use that in a second. Going back to our problem, if we find our differential dt, this is going to be -1 over x squared over 1 over x dx. And we can sort of simplify this in my opinion. This is going to become -1 over x dx. All right, not bad. So now we have n factorial is equal to integral from, we got to change our parameters here. So when x was equal to 0, our new parameter is going to be natural log of 1 over 0, which is going to be undefined. And if you kind of know the graph of natural log, you know that this is going to approach infinity. And now when x is equal to 1, we have natural log of 1 over 1. Well, that's just going to be 0. Okay, so our properties or our parameters are going to change. Now we have infinity to 0 of this particular function. Right now we have t to the power of n times our dx, negative x dt. But now we still have a integral that still has the x. Well, let's go ahead and take a look at this value here. E to the t is equal to 1 over x. So guess what? We can go ahead and also say that e to the negative t is going to equal to x. And now we found the value for our x. We're going to go ahead and plug that into our integral there. So now we have n factorial is equal to, let's go ahead and bring that negative sign that's inside the integral to the outside. And that's going to give us negative infinity to 0 of t to the power of n e to the negative t dt. Okay, but because we have a negative on the outside, we can just go ahead and flip these values. That's one of the properties of integration there. And this is going to become n factorial is equal to integral from 0 to infinity of t to the n e to the negative t dt. So now we found this really nice integral, an integral from 0 to infinity of t to the power of n times e to the negative t dt is equal to this n factorial value. And this is really nice because we would not have been able to solve this using the basic or the original integration techniques that were taught in calculus class. But now we know this really fascinating property that this integral here is equal to n factorial. That's pretty freaking nice. Well, because this is so nice, we have to name it something. I mean, it has to have some practical use. And this is the gamma function. So this right here, gamma of n plus 1, is defined as n factorial, which is equal to this integral from 0 to infinity of t to the power of n e to the negative t dt. We can go one step further, and instead of using gamma of n plus 1, we can go ahead and use gamma of n. So we're really just subtracting an n there, which is going to equal to the integral from 0 to infinity of t to the n minus 1 e to the negative t dt. And this is going to equal to n minus 1 factorial. How sweet is that? Now, we're definitely going to cover more properties of the gamma function because there's a lot to do with it, but I think this will be a good introduction so that whenever we do see problems involving the gamma function, we can just go ahead and revisit this video so that you have a good refresher. All right, guys, take it easy.